Welcome to synthesis and analysis of an iron coordination compound. This is probably the most fun lab for the semester and is also the culminating experience for the semester. In this lab, we do pretty much everything we've done this semester. We synthesize something, and that synthesis has gases and color changes and precipitates and anything you could hope for. We vacuum filter things using the Buchner funnel. We titrate using a dark purple liquid. And we use the balances. It's just a lot of fun. So we're going to get started talking about two things today. The concept video, and this concept video will be for both this week, the preparation of this compound, and next week the analysis of this compound. So it's going to be longer than normal. I'm also going to include the calculations for this week, and that's important because they're part of your pre-lab, so your pre-lab quiz. So this is going to be a long video. Hang in there. We'll get through it, and hopefully you'll learn lots. So here we are, synthesis of an iron coordination compound. There are different types of compounds, and this one is a hydrate, which means it has these three waters. Now notice there's a little dot in there. Those three waters are not chemically attached to this coordination compound. They are trapped in its three-dimensional structure. All right, so this is an ionic compound. It forms a crystalline lattice, and in the pores of those crystalline lattices, it captures and holds these waters. So that's called a hydrate. Now, this compound is called potassium tris, meaning 3, oxalato. Oxalate is C2O4 2 minus. All right, so tris, oxalato, ferrate, trihydrate. And I should say ferrate 3 because this is iron 3 plus, trihydrate. So it's a long word, potassium trisoxalato ferrite trihydrate. So we lovingly call this Green George. So that's pretty much what you're going to hear me calling it. I'll occasionally spit out this long name, but Green George is simpler, and it is a bright, bright green crystal, so you'll see why we call it that. All right, so the first thing we're going to be doing is making this, and all of the details that are associated with a synthesis we're going to see this week. So we're going to start with this pale aqua crystal. That's ferrous ammonium sulfate hexahydrate. And oxalic acid. This is oxalic acid. You can see the oxalate right in there. Now, upon adding the oxalic acid, this iron coordination compound, this is another one, is going to break apart and reform iron oxalate. Now, oxalate is 2 minus, so this iron is 2 plus, so iron 2 oxalate. Okay, first concept that we remember, oxidation numbers, iron 2 oxalate. And sulfuric acid, you should begin to know these names. Sulfuric acid, the acids you should know, especially strong acids, and ammonium sulfate. When we look at the name for the product, it says ferrate 3, which means this compound, Green George, has a 3 plus iron in it, different oxidation state from the one we have now. So that's our second step, using hydrogen peroxide as an oxidizing agent, which means it's being reduced and forcing the iron to be oxidized. We have 2 iron, 2 pluses yielding 2 iron 3 pluses and 2 electrons. Remember, these are our half reactions. Meanwhile, notice we've lost one of the H pluses off of hydrogen peroxide. Water and the HO2 minus plus 2 electrons becomes 3 hydroxides. Right? Balanced chemical equation now. Here is our balanced net ionic equation, in which the iron 2 plus is oxidized to become iron 3 plus. So that's step 2. Step 3, which happens immediately after step 2, and there's not much anything you can do to stop it, is that the iron 3 plus and the hydroxide very quickly form this iron 3 hydroxide solid, and it's brown and clumpy and disgusting. So the iron 3 plus and the hydroxide combine to form iron 3 hydroxide, which is a solid. Fourth step, we're going to use potassium oxalate and the iron 3 hydroxide and oxalic acid to form our product, potassium trisoxalato ferrate 3 trihydrate, or Green George. Okay? Now, this is aqueous, notice. And we need to make this a solid in order to mass it and find the theoretical yield and to analyze it next week. So in water, this is very soluble. But remember, water is a very polar solvent. So if we change, and this is an ionic compound, like dissolves like. Ionic compound, which is extremely polar, loves to dissolve in water. Okay? So what we need to do is make this solvent less polar. And if it's less polar, then it won't dissolve the ionic compound. And we're going to change the polarity by adding ethanol to it, quite a bit of ethanol to it. And that will force this to precipitate out. So we're going to go into this step with a bright green liquid, and at the end of this step, we're going to have a bright green solid. At that point, we're going to use the Buchner funnel to dry it out the best we can, and then put it in a desiccator and store it until I get a chance to read it later in the week. Now, the big trick for all of this, which you may have already noticed if you glanced at your pre-lab quiz, is we need to know the stoichiometric ratios for all of this. Now I'm going to find my stoichiometric ratios. You're going to find the theoretical yield, and you're going to find the percent yield. So we're doing stoichiometry. So in order to be able to do this, we have to know our stoichiometric ratios. We have to know our molar ratios. So this effectively is our starting point. This is our product. Let's follow the iron. So we have 1 mole of the ferrous ammonium sulfate gives us 1 mole of ferrous oxalate, or iron 2 oxalate. 1 mole of that, 2 moles, of the iron 2 plus gives me 2 moles of the iron 3 plus. 2 moles of the iron 3 hydroxide, which results from this, forms 2 moles of the Green George compound. So as an example, we're going to start with 1 mole of the ferrous ammonium sulfate. Our first molar ratio is going to take us to 1 mole of the ferrous oxalate, or iron 2 oxalate. The next step takes us from our oxalate, in which it's 2+. So I'm going to go ahead and put that in. 1 mole of iron 2+. I'm going to have to start writing really small. Per 1 mole of ferrous oxalate, or iron 2 oxalate. Now 1 mole of iron 3+ per 1 mole of iron 2+, or that was a 2 to 2. And 1 mole of Fe, iron 3 hydroxide, per 1 mole of Fe3+, times, we're getting there, 2 moles, and I just have run out of room, so I'm going to call it Green George, per 2 moles of Fe, iron 3 hydroxide. Okay, let's check and make sure that everything cancels out here. 1 mole of ferrous ammonium sulfate cancels with 1 mole of ferrous ammonium sulfate. 1 mole of iron 2 oxalate cancels with 1 mole of iron 2 oxalate. Obviously, this should be answering one of your questions on your pre-lab quiz. 1 mole of iron 2+ cancels with, this was a 1 mole. Well, no, it cancels with moles of iron 2+. Moles of iron 3+ cancel with moles of iron 3+. Moles of iron 3 hydroxide cancel with moles of iron 3 hydroxide. So after all of this conversion, you're going to end up with moles of Green George. Every mole of ferrous ammonium sulfate should generate 1 mole of our product. How are we going to analyze this? How are we going to figure out if we actually got the potassium trisoxalato-ferrate 3-trihydrate? We're going to be using a redox titration. Oh yeah, oxidation reduction again. Now, when we put this compound in water, remember I said it was soluble in water, we're going to end up with 3 potassium ions and an iron 3+ ion and 3 oxalate ions and 3 waters. Okay, that's what we're going to end up with. The first titration, this is a redox titration, we're going to be using to analyze how much oxalate we've got. We'll know the molarity of our titrant. We'll know the volume of our titrant. We can get that from the burette. And we'll be able to figure out the moles of oxalate from that. Once we have removed this from solution, we can actually use the exact same titrant to work with this. Now, it's not going to be in this form. Don't worry, I'll explain it in a minute. But we're also going to use it to figure out the number of moles of iron. Finally, the way we're going to figure out whether you have Green George or not is to see the ratio. Is the ratio of oxalate of your compound to iron 3 to 1? Ordinarily, one of you would be standardizing the titrant, and one of you would be making the potassium trisoxalato-ferrate 3-trihydrate, the Green George. This is on a normal semester when you have a lab partner. Well, you don't have a lab partner, so Mr. Perueta instead standardized the potassium permanganate for you. However, you still have to calculate what its concentration is. We're not going to give that to you. So you have all the data and just have to do the work. But in order to figure this out, we need to know the equation. Now I want you to remember that the concentration of KMnO4 is equal to, in water, the concentration of K plus, and it's also equal to the concentration of permanganate, right? There's one ion of each of these. Similarly, the concentration of sodium oxalate is equal to the concentration of oxalate. All right? What we are going to be doing in order to detect the endpoint without using an indicator, because we don't need an indicator, we're going to use a color change. In MnO4-, the oxidation state of manganese is 7+. We're going to be changing that oxidation state. So let's take a look at what is going to happen. The permanganate in an acidic solution is going to be reduced to Mn2+, and obviously some waters. Now let's see if we can figure out how many electrons we're going to need. Remember, this is 7+, and this is 2+, right, 5 electrons. At the same time, we're going to be dealing with the oxalate. And oxalate is wonderful stuff. It oxidizes very quickly to carbon dioxide and 2 electrons. Cool. So now we have our half reactions. This is the reduction. This is the oxidation. We got to put this together to make our net ionic. These do not cancel. So we've got to multiply the top equation by 2. We've got to multiply the second equation by 5. So let's go ahead and do that. I have multiplied everything in the top by 2, everything in the bottom by 5. My 10 electrons cancel, and I get, for my net ionic equation, which is what I care about, 2 permanganate plus 16 acidic protons plus 5 oxalates yields 2 manganese 2 pluses plus 8 waters plus 5 carbon dioxides. Now obviously I haven't put in the states. This is aqueous, 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 liquid, gas. We can see that the permanganate got reduced. We can see that the oxalate got oxidized. This is not helping. Well, it helps to a certain extent. It allows us to figure out the stoichiometry, but what it doesn't help with is how are we supposed to know when we have consumed all of that oxalate? There's no indicator. Remember, the end point, the equivalence point, is where you have the same number of moles, or the stoichiometric ratio of moles of permanganate and of oxalate. Well, this is kind of cool. This guy is colorless. Okay, no color at all. And we know water and carbon dioxide have no color. So over here, the whole product area is colorless. Over here, these two are colorless. But permanganate is dark purple. So what is going on here? Remember, this is your titrant. You know the amount of moles of this, and you're adding titrant to it. So 1 drop of permanganate, or 2 drops of permanganate, react with 5 drops of oxalate, and it goes colorless. 100 drops of permanganate react with 500 drops of oxalate, and it goes colorless. And that continues to happen in a 2:5 ratio until all of a sudden we've used this all up. And when we've used this all up, that permanganate stays unreduced, I guess you'd say. It stays in its permanganate form. It stays dark purple. Now, I do not want any dark purple solutions because that means you've got a boatload of this too much. 1 drop too much should yield a pale pink, almost like phenolphthaleins, a pale pink endpoint. We're talking pale pink. Concepts for the second week, we're actually going to use that potassium permanganate, whose concentration we now know. And like I said before, the molarity of the potassium permanganate is equal to the molarity of the permanganate ion, 1:1 molar ratio. We're going to be using this to titrate our potassium trisoxalato ferrate 3 trihydrate. Each sample, like I mentioned before, is going to be titrated twice. First, to analyze the oxalate, and then to analyze the iron. Okay, so you're going to take a mass of your product, and the first thing you're going to do is dissolve it in water and add some acid, and then you're going to titrate it with the permanganate. 2 permanganate plus 5 oxalate plus 16 hydrogens yields 8 waters plus 2 Mn2 plus 10 carbon dioxides. You know your molarity, you know your volume from the titration, so you'll know the moles of permanganate. Now you use your molar ratio to find the moles of oxalate. And that's where you're going to stop, because all we care about to analyze this is the molar ratio of iron to oxalate, or oxalate to iron. So that's the whole point of the first titration. Now, in the second titration, I'll draw a line here. The second titration, remember, permanganate is an oxidizing agent. It forced the oxalate to oxidize to carbon dioxide. It's going to force the iron to be, wait a minute, right now our iron is 3+. Can that iron be oxidized? Is there an iron 4+ or 5+? No, there isn't. So the first thing that needs to be done is that we need to reduce the iron. Oh, for crying out loud, yes, we need to reduce the iron, and we're going to do that with zinc. Okay, so zinc is itself going to be oxidized, and the iron, which is in Fe3+ state, is going to be reduced by that zinc to iron 2+. And that we can titrate. Okay, getting this all balanced, our net ionic and that's the point of throwing in some zinc. That's the whole idea of putting in the zinc. Now, what happens is that iron 3+ is yellow. Okay, iron 3+ is yellow, and when you add the zinc, iron 2+ is a very, very, very pale green, but it's going to appear colorless. So you're going to add zinc and react it until the yellow is gone. At that point, you have to filter off the remainder of the zinc, or it'll totally interfere with the next portion of the reaction. Now, you're going to filter this, you're going to have it nice and clean, and you're going to, I'm not going to do the half reactions again, I'm just going to write down what our oxidation reduction is going to happen now. So this again is the titration. Whoops. So this is the prep for the titration. Now that we have the iron 2+, we're going to titrate it with permanganate. Okay? So without taking you through all the redox steps again, this is the reaction. Remember, I've now converted all that iron 3+ to iron 2+. And again, I know the volume from the titration, from the titrant volume. I know the molarity, so I'll be able to find my moles of permanganate that I've used. Using my molar ratio, I'll know my moles of iron. And that's what I care about. So now I know my moles of iron, and from before I know my moles of oxalate. Let's balance this. Let's see, we'll have 3, this is when it dissolves in water, 3 potassiums, 3 waters, 1 iron 3+, and 3 oxalates. That means our molar ratio should be 3 oxalates to 1 iron. And we'll see what yours is. We'll use those 2 results that we got from the titrations to hopefully see that yours is a perfect 3. Okay, part 2. Don't worry, this part's a little bit shorter. Now I've put some fake data in here so we can actually do some analysis, some theoretical yield of the potassium trisoxalato ferrate 3 trihydrate. So I masked the ferrous ammonium sulfate at 5.1321 grams. Now my molar mass of this substance is 392.14 grams per mole. So 5.1321 grams times 1 mole over 392.14 grams gave us the number of moles of 0.013087. Lots of sig figs, 5 here, 5 here. Now I masked my beaker, and then I had Mrs. French mask my beaker and Green George once it was dry. And the difference between these two is 5.5230, and that's what my actual yield of the potassium trisoxalato ferrate 3 trihydrate was. So I now need my molar mass, and this is 491.25 grams per mole. So again, I multiply my grams times 1 mole over 491.25, and I find that my number of moles is 0.11244. Now the theoretical yield. The theoretical yield, remember, I got from my moles of ferrous ammonium sulfate, and the molar ratio, so 0.013087 moles of, we're going to call this star because I'm going to run out of room, is what I started with, times 1 mole of ferrous oxalate over 1 mole of starting material. So our starting material moles cancel, times 2 moles of iron 3 hydroxide over 2 moles. I'm skipping a step, combining 2 steps, of iron 2 oxalate, moles cancel, times 2 moles of the potassium, trisoxalato, oh my goodness, ferrate 3 trihydrate per 2 moles of iron 3 hydroxide. My moles of iron 3 hydroxide cancel. And if you do that whole thing, it comes out to be 0.013087 moles of, I'm going to call it Green George. Of Green George. Okay, so what mass does that end us up with? Well, again, we'll use the molar mass, and we will find that this was 6.2981 grams of Green George. So this was what I was supposed to get. That's my theoretical yield. This was my actual yield. So my percent yield is just actual divided by theoretical times 100%, or 87.702%. All right, you're going to need to be able to do this for your pre-lab quiz and by the end of this lab. The other thing you're going to have to do by the end of this lab is this calculation. Now, let's put this reaction back up. So there's our reaction. So let's do this. We know the moles of the oxalate right here. So this moles of sodium oxalate equals moles of oxalate. So there they are, and that should be a 6 at the end. Now we know our milliliters. So we know our moles, we got to use our molar ratio, and then our volume will give us our molarity, right? We already decided that. So our volume, obviously, since we started, Mr. Peretta started at 0 every time, is 31.40 milliliters, 31.90 milliliters, and 31.09 milliliters. So at this point, I'm just going to go ahead and do one example. So we have this number of moles. So 0.000155 moles of oxalate times, let's see, our molar ratio. We're going to permanganate, 2 moles of permanganate. Sorry, I'm totally out of room. Per 5 moles of oxalate. Moles of oxalate, 2 minus. Moles of oxalate cancel, and our moles of permanganate, 6.224 times 10 to the minus 4th moles. Now the last thing you have to do to get to molarity is to change your volume from milliliters into liters, which you should be able to do without batting an eye now. And then molarity is moles per liter. So that tells you how to get to the last step. And when we divide 6.224 times 10 to the minus 4th moles by 0.03140 liters, That equals 0.01982 molar. Now you're going to do the same thing for the rest of these, and then you're going to average them to find your average molarity. And that we're going to use next week in the calculations for the last week of Green George.